In the beginning was the Big Bang. We are told that 13 to 20 billion years ago, everything that makes up the universe as we know it was spontaneously created out of nothing through an unimaginably violent explosion. But did it really happen as we are told? A growing number of astronomers doubt it and are showing why. This is their story, the story of the universe.
The observational aspects of trying to understand the universe, I think it's reasonable to start about 100 years ago. And about 100 years ago, almost everybody in astronomy, without question, assumed that the whole of the universe was what you could see in the Milky Way. Nobody felt that the universe was any bigger than the stars that you see in the sky, associated with our own local Milky Way. And that was the situation certainly around 1905, times like that. There are well-known people who propounded these ideas. 10 years later, Einstein first proposed his general theory of relativity. Now, when Einstein proposed this, it's a theory of gravity, which means that it's a theory which should represent the whole of the universe, because it's gravitational forces that are controlling the universe. Well, Einstein made this theory around 1915, and he immediately wanted to try and use this theory to explain the universe as it then was, the so-called Milky Way system. But of course, the idea of this was that it was a static system. That is, it wasn't contracting or expanding, it was a static system. And Einstein found that his equations did not allow for a static universe unless he inserted a certain constant in the mathematics, which became known as the cosmological constant. But what happened in the early 1920s was that a very clever Russian called Friedman in 1922 found solutions to Einstein's equations which allow the universe to either expand or contract. Now that was done in the Soviet Union soon after the revolution, and nobody in the West knew about this, I think. But in 1927, a Belgian priest, the Abbé Lemaitre, as he later became, also discovered these solutions. And he went to England, and his work was publicized in Cambridge and elsewhere, and the famous English astronomer Sir Arthur Eddington and others got to know about this, and they immediately began to say, how can this apply to the current universe? Well, in the same period, in 1929, Hubble made what I still believe was the most important discovery in extragalactic astronomy in the last century, or the last century but one. He showed that if you look at the spiral nebulae, the faint spiral nebulae, the shifts in their spectra are proportional to their apparent brightnesses. And this led very soon to the idea that this fitted very well with the expanding universe, and that indeed this is the kind of universe we lived in, that what we were looking at are galaxies, Milky Ways, further and further away from us, and the further away from us, the larger the redshifts, and if that's interpreted in the way that most people would interpret it, this means that they are moving away faster and faster. So this was the original idea. By the 1930s, the front page of the New York Times said we live in an expanding universe.
When Hubble made his great discovery, it was for galaxies like our own Milky Way galaxy, and they all followed the same rule, that the fainter they are, the larger their redshift. In other words, the faster they are moving away from us. This is known as the Hubble law and directly led to the expanding universe theories. But in the 1960s, there was a new discovery, the quasi-stellar objects, often referred to as quasars. They appear as star-like points on the sky, frequently blue in color, and they have very, very large redshifts, implying that they are at huge distances from the Earth, at the very boundaries of the observable universe. Some astronomers soon found that a vast number of these strange new objects populated the regions around spiral galaxies, and were not only observable with radio telescopes, but were optical and X-ray sources as well. There were two properties of the quasars that were difficult for astronomers to understand using the expanding universe theory. The first was that if one plotted their apparent brightness against their redshifts, as one does for galaxies, one gets an unexpected scatter on the diagram, instead of the smooth curve made by the same plot done for galaxies. This seems to indicate that the quasars do not follow the Hubble law as do most other objects, and that there is no direct indication that they are actually at their proposed redshift distances. In fact, it is argued that if Hubble had first been given the plots for quasars, he and other astronomers would never have concluded that the universe was expanding. The second property was that quasars are very small, compact objects, sometimes only a light year across. So if quasars are really at their extreme redshift distances, they must then be the brightest and most energetic objects known to astronomers. So energetic, in fact, that untestable, almost metaphysical mechanisms must be applied to explain the phenomena. On the other hand, when placed at their observed distances, that is, in the neighborhood of nearby galaxies, their brightness and energies become normal, and no special mechanisms need to be evoked. This problem has led many astronomers to abandon the idea that all redshifts are due to their speed of recession away from the Earth. And if this is true, then there is no need for an expanding universe, and the Big Bang never happened. The questions arise. Is there a connection between certain types of galaxies and the quasar? Are quasars ejected from galaxies, and in fact proto-galaxies themselves? Is there some other astrophysical process which can explain the redshift discrepancies? One of the world's most controversial experts on the structure and morphology of quasars, Halton C. Arp, has for 35 years proposed just such an idea. For the heresy of opposing orthodox interpretations of the redshift problem, Arp has had to pay a heavy price, the same price paid by many a scientist with new and innovative ideas. Dr. Arp was forced to resign from his permanent position at the Carnegie Institute of Washington Observatories after the Caltech head of the Telescope Allocation Committee threatened him by saying, unless he changed his line of research, they would take away his telescope time. Due to this fact and his ongoing struggle against the established paradigms, Arp is often referred to as the modern Galileo.
I remember when I sent the paper into the first paper into Astrophysical Journal on the nature of companion galaxies, and I had a lot of them on the ends of spiral arms, so I was sure that they were connected, and I showed that they were systematically redshifted. I sent that in with naive, great expectations that people would be terribly interested and impressed on this. And the editor of the Astrophysical Journal at that time was Subrahmanyan Chandrasekhar, who had a fantastic reputation as a master theoretician and also quite an incomprehensible theoretician, and a tremendously powerful figure in the field, and editor of the Astrophysical Journal, which was probably the most powerful position in the field. And he chose not to, in his wisdom and judicial fairness, chose not to send it to a referee, but he just wrote across the paper, "This exceeds my imagination," and he sent it back to the director of my institute, Horace Babcock, with the obvious implication, you've got to do something about this staff member of yours who's doing these very bad things. And so Horace called me down in the office one day after this, and I walked in his office, into the director's office, and I saw this paper lying in front of him with Chandrasekhar's scroll across it. And Horace looked at me and said, "Well," he said, "this is just too much, and you're going to have to start looking for another job." And so all I could say to him was, "Well, if you send me that in writing, please send me in writing." And I was waiting in great trepidation for weeks and months to get something in writing, and I finally never did, so I realized that he decided to give me another chance, so to speak. So that was fairly early in the game, and then some years went by, and there was the competition for time, particularly on the 200-inch telescope, was getting more and more heated, and people were saying, "Well, we can't continue to give time to this obviously incorrect and embarrassing research that ARP does." So finally they sent a letter to me from the allocation committee, including a number of the younger members of my institute, saying that unless I changed my line of research, that they would have to take away my telescope time. At that point, I considered the situation very carefully, and I figured that the evidence, although a lot more evidence could be gathered and has since been gathered since then, the important thing was not the evidence, because if it was true, it would come out someday. The important thing was the principle of scientific investigation, whether scientists could follow new lines of investigation and follow up on evidence which apparently contradicted the current theorems and the current paradigms. And I also felt that regardless of what happened to me personally, that this was the important issue, and that I had no choice but to resign on the point of this issue, so that if it developed, which I thought it would, that my line of investigation was correct, that people then in the future would say, okay, this was the wrong thing to do, and in the future we're going to have to see that this kind of thing doesn't happen again.
The observers come in now with the belief that we live in a Big Bang universe, and therefore all of their ways of understanding things are tailored to that. And they don't come in with the possibility that our alternative, or any other for that matter, is right, and really do it in an open-minded way. And of course what goes along with that is that observers who would like to test this way find it very hard to get observing time and so on. I mean, this relates to the whole issue of whether the complete lack of balance in the way the observational programs and the funding are conducted. There's no question about that. I don't think that anybody would argue about it.
I've always said that the cause of the troubles is the American graduate school. You get one person who then lectures to his students in graduate class, and because you have a system, you see, when we had graduated first degree, we were independent. We could thumb our noses at the professor, and in fact the best way to get ahead was to do something that the older people didn't agree with. Really? Right, that was the way to do it. And but in the graduate school, you all have to learn what you're taught, what the professors are teaching you, and then those people go out and get jobs, and they have another graduate, their own graduate school, and it just tier after tier. You get a few places like Caltech or like Harvard, and they set the fashion for every place.
I think there's a problem with graduate education. I think graduate education is not teaching students to think, to be independent researchers. I think it's teaching them to be part of a scientific society. And too much, especially students that are at the so-called elite institutions, I think they're taught too much the paradigm of their advisor.
All of us, whether or not we served in uniform, are veterans of a war in which freedom and free government are at stake. Such fullness of knowledge is the direct function of education. Most of us work hard to provide our homes with every possible comfort for our children. We safeguard their health. We strive to set before them good examples of moral living, of manners and deportment. Possibly, we even pamper them. Yet complacently, even carelessly, we commit our children to schools of which we know but little. We cannot meet the complexities of modern life with outmoded school systems. We must keep our educational standards abreast of the swift-moving times in which we live, if we hope to preserve our national heritage and our American way of life, the American way.
When I was director of the National Observatory 20 years ago, there was a very well-known astronomer now. In fact, she's just won the Cosmology Prize. That's Vera Rubin. She was carrying out a program at Kitt Peak at the National Observatory of observing faint spiral galaxies with a view to looking to their redshift distribution, their velocity distribution. And this was a program that everybody thought was a good program. And so she'd been given observing time, and at the end of about a year, she had completed about a third of her program. And so she actually wrote a little paper pointing out that she was getting results very different from the ones that were expected. And we had our usual meeting. And when we got to her program, which was an ongoing program, so people just looked it over, the leading extragalactic astronomer on my committee of that day immediately said, well, look, she's getting this result. It doesn't fit. It has to be wrong. I recommend that we stop the program. That was his position. And what was interesting to me was I sat there and listened to this discussion. And the majority of the people, because of his level of knowledge and authority, went along with him. So the recommendation of the committee was that we stop the program. Well, I had the last word, so I ignored it. But most people don't. And the peer review system and NASA itself, which is very conformist, will always do just that. That's one of the reasons why the road ahead is hammered out. As Hoyle said, anytime you point a new telescope at the sky now, you're only going to find what you already know is up there.
I have a lot of trouble with the academic world, the same as I do with the Bible Belt. It's the same kind of trouble. It's the same kind of trouble. It's because they get a picture of this world which they are sure is right.
Yes, yes.
And they hang on to it for all they're worth. But you know, I often point out that I am probably more unorthodox than anyone who has ever burned at the stake. It's illegal now.
Illegal burning.
It's illegal now to burn somebody to the stake in your backyard.
Peculiar galaxy NGC 7603, discovered 30 years ago by Halton Arp, is one of the more striking examples of galaxy-quasar connections. It has recently been re-examined after the discovery of 2 new quasar-type objects embedded in the connecting filament. The renowned optical astronomer Margaret Burbidge has for decades been a central figure in the struggle to bring controversial observations such as NGC 7603 to the attention of conventional astronomers. And for her fairness and untiring efforts in the field, she has become one of the most widely respected women in astronomy.
There's a very interesting galaxy known as NGC 7603. It's a Seyfert galaxy. That means it has one of these active nuclei with strong emission lines and a lot of activity, obviously, going on in its center. And it was studied years ago by Chip Arp in his Atlas of Peculiar Galaxies. It has a spiral arm that seems to come right outside of the galaxy, trailing right out, and it ends up on a fainter galaxy, but it ends right up as though it's connected the nuclei of the two galaxies.
In the Atlas of Peculiar Galaxies, which was published in 1966, that was the point of the atlas, and one of the objects, just to illustrate what a peculiar galaxy is this what is now famous NGC 7603, and this is the central Cepher, which means just a very, very active galaxy with a lot of energy in the nucleus and a lot of explosive energy and so forth. And here is the high redshift companion here, and you see it's joined by a filament, a material. It turns out, from the observations, that this filament of material is material of the galaxy, gas and dust and stars and so forth. It's been drawn out in the ejection. But the astonishing thing and the controversial matter is that this galaxy is a much higher redshift than this.
Now, NGC 7603 has one redshift of about 8,000 kilometers a second, and the other galaxy has a much larger redshift. So how can they be connected? Well, these data were published years ago, and everybody said, well, this is just a chance location of a background galaxy near an interesting foreground galaxy, and that spiral arm has nothing to do with it. It's just the whole thing is just a chance.
If you see two objects close together with very different redshifts, you only have one of two explanations. One is, as I say, that a large part of the redshift has nothing to do with distance, and the other is that it's an accident. So the real issue that you come down to is how frequently do you expect to see accidents?
If you look carefully at the pictures that were taken of this field, you will notice two faint stellar objects that are in that spiral arm. One is close to NGC 7603, and the other one is close to the faint companion galaxy.
In the year 2001, when the two young Spanish astronomers worked on this with the Las Palmas telescope, they saw that there were these two condensations, stellar condensations. They looked like quasars, but everybody would have said that they had to have the same redshift as the central galaxy because they were obviously in this filament that had been ejected. What they found was that each of these objects had a much higher redshift, and that the filament itself had the same redshift and spectral composition as the galaxy from which it was ejected.
And they got some spectra using what's called the Nordic Optical Telescope in the Canary Islands on La Palma. It's not a very large telescope, but they got some excellent data, and they got spectra of these two faint objects, one by 7603 and one by the companion galaxy, and believe it or not, they showed that both of them were quasars. Not very high redshift quasars, but definite quasars.
Two of these quasars. Now this one will turn out to be quite good, but it's a very nice.
It's a fairly big blow-up. This is only a couple of arcs that can cross. But it looks like it's extended.
Anyway, it looks redshift.
So we'll go ahead and move it and then narrow it up.
The chance to have many quasars around a galaxy as a background objects. Of course, you have some chance, but these are very, very low, and this is what what should be answered. This is what should be answered. NGC 7603 is a very special case of this correlation. You find not only three objects with different redshifts in the neighborhood of a major safer galaxy. You also find the filament connecting all of them. So this is more important because the probability to have all these objects, not only in the neighborhood, but exactly in the filament is extremely low.
The galaxy, which is an active galaxy, two low redshift quasars, and another galaxy with twice the redshifts. In other words, you had four objects all connected together, apparently, by a luminosity, by a luminous bridge, each with a different redshift. Now that, I would say, is pretty conclusive evidence for the existence of non-cosmological redshifts.
We were lucky because we have found that the object has more controversy than expected. If in the past Chip Harper thought, and Barbies and all other people that have dedicated an effort to research this object, if they thought that there were two objects connected by a filament with different redshift, now we have discovered that there are four objects all connected by the same filament and all of them with very different redshifts. So the Doppler redshift is discovered.
I think they have to look at it, and I think it's one of the most striking results that we have available. How they can make sense of it other than saying that these objects, that these redshifts of connected objects that are the same, more or less the same distance from us, that these redshifts have non-cosmological components to them.
The topic of the anomalous redshift is very important for most of the areas related with cosmology and extragalactic astronomy nowadays. If we assume, as it is done nowadays, that all the redshift are pointing the distance of the galaxy or the quasar or whatever, of course the results will be very different than assuming the other thing, that the redshift are due to other reasons. The distance of the quasars and the galaxies will be different, the energies involved in the process will be very different, so a lot of astrophysical processes will have to change.
Conclusive evidence that the expanding universe was not correct, and that the redshift distance law was not correct, and that we had to have some way of creating new galaxies with high redshifts.
It is normally argued that the Big Bang, for instance, the Big Bang cosmology, is against the anomalous redshift question. And of course, the Big Bang theory is the most important theory that we have nowadays to explain all that we know about cosmology, which is not too much, in my opinion.
There's a large body of work going on, observational work, theoretical work, which is based on the assumption that quasars are at their cosmological distances. If it turns out seriously that we're right, then all that work is in vain. We don't know anything like as much as we think we do by saying that the quasars are far away. And that's another huge problem for people to face up to.
One of the frightening things, I think, for conventional astronomers is to accept the fact, or to realize that these intrinsic redshifts for the quasars and peculiar galaxies and so on, active galaxies, means that a lot of the things which we thought were out at great distance in the universe are very much closer in. And in fact, you would have to say that what we call the local supercluster is much more crowded and contains many more objects than we previously thought. And then the question comes up, well, what is out beyond the local supercluster, and can we with any certainty identify any objects that are out there?
Aware of what of our interpretations, because we cannot distinguish which objects have cosmological redshift and which objects have non-cosmological redshift, then we cannot trust the redshift indicator as a distance indicator.
People who work on the origin of the universe, they ought to look at data of this sort, because they've got to understand this. And I've heard good friend astronomers say, well, there's more out there in the universe than we understand.
What's really happening in these systems is that the centers of the galaxies are the places where creation is taking place rather than just in a big bang. And so you're looking at all these mini bangs where matter and energy are actually literally being created. And this is an old idea which is not ours. Originally it was due to the very famous Armenian astronomer Victor Ambatsumyan, who only died a few years ago, who also argued that galaxies which appear to be coming apart and objects that are coming out of them are coming out of them. Very simple idea, but Ambatsumyan, who was a very well-known theorist, always said you must look at the observations, and maybe if things are coming apart, appear to be coming apart, maybe they are coming apart. Conventional astronomers don't allow things to come apart. They always say there's enough dark matter in the system to hold it together.
I've come to the conclusion that what it is that will unseat an established prejudice, a strongly established prejudice, is one observation. One single observation, usually a very simple one.
The conclusion was very, very strong just from looking at this picture, that these objects had been ejected from the central galaxy and that they were initially at high redshift, and the redshift decayed as time went on. And therefore we were looking at a physics that was operating in the universe in which matter was born with low mass and with very high redshift, and as it matured and evolved into our present form, that we were seeing the birth and evolution of galaxies in the universe.
If protoquasars ejected from the nucleus of active galaxies themselves evolve into new, younger galaxies, astrophysicists must find experimentally and observationally the mechanisms which describe this phenomena. One model explains that the protoquasars are ejected, trapped in the galaxy's extreme magnetic field, aligned along the spiral arms, thus explaining the torn, disturbed features often observed in the galactic medium, and the frequent appearance of high redshift companion galaxies attached by filaments to a lower redshift parent galaxy. The other and most frequently observed alignment is when quasars appear to have been directly ejected out of the galaxy's active nucleus along its line of least resistance, creating a field of systematically high to low redshift quasars, or younger to older evolved protogalaxies. This is exemplified in innumerable systems like the one around the galaxy quasar field of NGC 3516. If one disregards the proposed redshift distance to these objects, observation clearly points to ejection as a likely explanation for their close vicinity to the central galaxies around which they are found. These results, though preliminary, are promising developments which may lead the way to new and exciting insights in cosmology.
One of the best and earliest of the really controversial things was a Seafoot galaxy known as NGC 4319, which Chip Arp discovered that it has a protrusion coming out in the south direction from it, one of its spiral arms, and ending up on another galaxy known as Markarian. And people have tried to explain it away in all kinds of ways, and tried to take false pictures to show that it's not there. But I've seen the good pictures, which were the first really good pictures were taken by Jack Solentic.
NGC 4319 was part of some work that I did in the early 80s when I was a young astronomer, a young faculty member, and people were coming up to me and saying, oh, I've written a paper to show that what Chip Arp has done is wrong. There were at least 3 famous papers right around 79, 80, 81, and it took about 5 minutes to look at these papers to see that they they were flawed. And one of them was a paper that claimed to show no connection between NGC 4319 and the quasar Markarian 205. So at that time I had the opportunity to work at JPL using the new image processing facilities that had been developed for the Voyager program, in fact. And it took 1 hour's effort to show that there was some kind of a luminous feature between those two objects. I don't know what it is, but there's no question that there is a luminous feature, and it cannot be dismissed in the ways that it was dismissed in the early 80s.
Suddenly there appeared press releases from Space Telescope Science Institute, which was the research arm of NASA's Hubble Space Telescope, and this press release said that they were not connected, and it gave a Hubble Space Telescope picture. It was not very deep, and you could just see two objects and no connection between them. And in this press release, then they said that that this proved that there was no contradiction with the current expanding universe paradigm.
No connection between the two objects. So I looked at their picture, then I downloaded it, and it took me 5 minutes to show that it's still there. Now, I don't know what it is, but I think you face up to the existence of the feature, and then you consider conventional and unconventional explanations. But I was really surprised that they felt it necessary to issue a press release saying, it's not there, it's not real. It's the same thing we saw 20 years ago.
But it's hard to get people to look at this because they don't understand it. You see, it's again the non-cosmological redshifts.
We realized that the people who had been processing the pictures and released it must have known that the bridge was there, and yet they chose to try to convince the public that that in fact it wasn't there and that everything was right with the current expanding universe paradigm.
It's a strange attitude. I don't understand it as a scientist, really. I think that news release could have generated much more interest in astronomy than many of the more conventional news releases, because people would be talking amongst themselves, gee, what could that be? And then various people could offer scientific explanations. But to just sort of close the door, in a way you could argue that Chip, or someone like Chip, who believes in an alternate interpretation, I'm sitting in the middle of the bridge, so it could be either way, he should feel strong, because I interpret that as a manifestation of fear and uncertainty. Because if I really had confidence in my paradigm, I'd put it right out there and say, well, yes, there is a bridge there, but it's either this explanation or it's that explanation, but certainly it's not what Shapar says. But instead to just say it isn't there, that's a manifestation of fear, I think.
This misrepresentation of the results on a public level, published through a press release from a government-supported institution, which was not refereed and which gave the wrong information, seemed to escalate, in my opinion and my colleagues' opinion, escalate the controversy into a publicity campaign, which was sort of like doing scientific research by press releases in an attempt to defend, as a sort of a last resort, a dying paradigm in physics.
I don't know what more one can do than the data are there, they've been got, we have to make sense of it.
I think in one sense they think it's bad to, quote, confuse, unquote, the public. Because if you believe in the standard paradigm with all your heart, you know it can't be real. I know it can't be real. You know, if I try to be at all rational within the context of the current Big Bang ideology.
So if you have a cosmological theory that actually starts somewhere. I mean, I knew this when I was 10 years old, I think, sitting out in the backyard swinging with my brother, thinking about what would the edge of the universe look like if we got to the edge of the universe. And we both of us realized, even at that age, that the notion was somehow did not make sense. The universe can't have an edge, and it can't have a beginning, because if it had an edge, there has to be something on the other side, right? And if there had a beginning, there had to be something on the other side of that. And somehow cosmology, a satisfying philosophical cosmology to me, would have to start with that notion that it was always this way and it always will be this way. There's all kinds of things happening in there, but somehow the basic laws of nature are such that this exists.
Of course, this is astrophysics, this is science, and everything can be refuted. You have an explanation, you can produce an opposite explanation, so not everything is not so simple.
The theoreticians ought to be really looking at this theoretical problem, and the observers ought to be gathering much more data of the sort that we get. But I think they're all a little scared because it's an unpopular subject. They're worried about their jobs, and they're worried about getting moving on up the ladder. You know, if they're postdocs.
A young person in academia cannot afford to go against the Big Bang. He'd immediately lose his position, tenure.
Tenure, yeah.
As I said last night. And so there is this difficulty. You can't expect them to do that.
Don't collaborate with Chip Arp, or don't collaborate with Geoffrey, because if you do that, you will have problems to get a position in such a place. I received such a blackmail.
When I was a student, I was naive, and when I saw the chance to work with Chip Arp, he sent me a letter. This is 30 years ago, in fact. Good heavens, I hate to even think that it's 30 years ago. And warning me now that you may find some people put off by an association with me. And I didn't even understand what he was talking about. I thought, I'm just trying, we're just looking for the truth, aren't we? We're just investigating other areas, alternatives. But I found, indeed, that it was not this way, and that there was a great deal of hostility.
In my opinion, even if we are wrong, I'm not saying that we are right or anybody is right. From an observational point of view, we have a very peculiar object. So, and this peculiar object, it deserves some further research. This is what we need. And the interpretations are free and are to be discussed.
Now we're entering the realm of cosmology, and it is here that religion, philosophy, metaphysics, and science all meet. And make no mistake about it, they all play a role in our beliefs. The amount of data that we actually have to support any particular model is small. It's mostly consistency arguments. We can argue that the 3-degree microwave background radiation, yes, it can be explained within a Big Bang context, but I believe Fred Hoyle and Jan Harlacher and Jack Burbidge have suggested an alternate explanation. And I'm sure we could find 10 more if the need were felt. But strangely enough, it's not. You don't get tenure in a university, you don't get promoted, you don't get recognition by looking too much into unpopular areas.
Cosmology is not a science. Has a lot of scientific aspects. We can know many things with the science. We can know how the galaxies are distributed, and these are measured with the observations. We can know how rich are how many metals are in the intergalactic medium or in some galaxy, and all these aspects are scientific. But with regard to some considerations about the beginning of the universe, this is in some way crossing the barrier of the science and going to something in between the science and metaphysical speculation, in my opinion.
Sociology is very important in science. People are in groups and gangs and cliques and clusters, and of course that enforces conformity. You want to be one of the boys, one of the, dare I say, one of the girls. It's the same after all. And so you tend to think alike. The longer you're together, the more you will think alike. I remember one famous group once, I asked them, how do you resolve disagreements amongst yourselves? And the reply was, we vote. And I thought, what a strange thing to do in science. Vote? I would think the best thing is that all 7 of you disagree. But there's a feeling that creates chaos. And the argument that we need some common thread or road to follow, for the majority to follow, in order to have some kind of organization to the whole scientific enterprise, there is an argument for that. But when it becomes all-encompassing, so that no other possibilities can even be explored, that is not good. And we're there.
Scientific notions take on, they have a lifetime of that really is involved in it gets involved with like somebody's job. It gets involved with, my theories are all in this particular, support this area. And so I don't want anybody in my department actually who doesn't work in that. I wouldn't want somebody in my department who was working in a very different side of things, like the steady state big banger kind of thing. If you were a steady state person, you're at this point you're feeling a little bit, paranoid anyhow, because most people said, hey, they found, Penzias and whoever he was, Arno Penzias, and the guy found there was the sky wasn't dark. There was a tiny little bit of light.
The cosmology as a science has begun 1 century ago with Einstein theory. So in 100 years, you cannot produce a theory of everything. This is crazy. Even from a philosophical point of view, historical point of view, we have begun 100 years ago. In 1920, we thought that the Milky Way was all the universe. And now you want to produce the belief that in 80 years or something you have produced the theory of all the universe from the beginning to now. This is somewhat incredible, and not very objective.
The Big Bang is predicated on the assumption that from a point of view of physics there are no surprises in store for us, which is very unlikely.
When you start using words like infinity and perpetual and steady state and all those kind of things, you're really using a vocabulary that was formed here in a quite limited sort of part of the vastness of everything, right? I mean, we developed that vocabulary as a way of finding food, mates, building shelters, that sort of stuff. We didn't develop that vocabulary from vast knowledge or need to know about how the universe works.
We're at the level of where the observations are clear, in my view, but the theory is not. And one of the things that you find in science, and particularly in astronomy, is that people find it very hard to believe in observations if they don't have a theory, if they don't have a theory ready to explain it.
We also need theoreticians. Observations without any theory don't work. And theory without any observations certainly don't work. And the problem is to get them together. The problem is to get them together. We need some glue.
To anybody with an open mind, that should really prove the case that quasars are associated with galaxies that must ordinary kind of redshifts, while the quasars have higher redshifts. Therefore, they must part of the redshift must be non-cosmological, not to do with the expansion of the universe.
Because I'm always thinking, if we can only be more rigorous, they will believe us. But I was wrong. I was very naive. It's got nothing to do with that.
The rolling of the Big Bang, it's largely been determined by the way people seized upon these ideas, and there's been tremendous amount of propaganda making claims that here we see everything happening and this has to be right.
The people that are in that field treat it like a religion.
And not very objective.
The reaction of the Orthodox astronomers to this idea is
that it violates the Big Bang assumption, the Big Bang hypothesis, and therefore it cannot be true.
The amateurs tend to be more broad-minded than the people who have to earn their keep by being narrow-minded. I got it.
Was this worked out by somebody, or was it, did it just happen by chance? Which is really the same thing as saying, did the universe happen by chance? And I have to say, when I look at it, it doesn't look to me at all like chance.
Imagine if every puzzle on Earth was solved, every why that we have pondered but could not answer for all our trying be mastered. Imagine if we all, God's ways, could clearly understand. Will this be reality, or is it just myth? Our thinking is like the streaming colored lights, flames flickering across the dark northern night. It was dark before we started thinking, and it will be dark again if we stop. Some claim that most questions in nature have been answered. Others think that we have only just begun asking. This is their story, the story of the universe.
Plasmas are found virtually everywhere. They're found in solid state matters at very low temperatures. A flame of a match, a fluorescent light is a plasma. Fire in your fireplace is a plasma. The aurora obviously is a plasma. The sun and all of the stars are a plasma. Lightning is a plasma. In fact, 99.999%, as Alfvén used to say, of all observable matter in the universe is matter in the plasma state.
A plasma is an ionized gas. It means a gas consisting of charged particles rather than neutral particles, which is the constituents of a normal gas. The charged particles are electrons and atoms that lack electrons. So it consists of negative and positive particles that interact with each other by means of electric and magnetic fields.
The term plasma, as applied to electromagnetics, was first coined in 1923 by the Nobel laureate Irving Langmuir to describe the experiments that he was doing at the time. Basically, plasma consists of charged particles, the electrons and the ions or protons that we know in nature. It can also include charged dust. And in Irving Langmuir's experiments with the charged particles, he noted that they acted almost in a lifelike manner. They tended to develop cells. They acted very much in a way that indicated that they might somehow be related to life. And for that reason, he borrowed the term plasma from the blood plasma.
A plasma is like a society of individuals where all the individuals are interacting with each other through complex interactions like media, newspapers, television, and so on. And the normal gas is like a society where the individuals simply basically don't interact or interact at very short distances, very local communities.
The first effort to understand how plasma functions in the universe, to understand the plasma universe, was Christian Birkeland, who at the end of the 19th century wanted to understand what is the nature of the aurora.
Birkeland ble interessert I nordlyset I begynnelsen av 1890-årene, og grunnen til det var utvilsomt at han arbeidet med katodestrålerør. Et katodestrålerør, det et vakuumkammer hvor man satt på en spenning. Når lufttrykket blir lavt nok, så går det en strøm igjennom. På Birkelands tid visste man ikke at det gikk en strøm, for man kjente ikke elektronene. Men allikevel så trakk han en analogi mellom disse katodestrålerørene og det som foregikk på sola.
At this time, people were studying, for the first time, the nature of electrons. And you had, for example, the development of the cathode ray tube. The cathode ray tube we're familiar with. This is what powers our computers and our television screens. You have electrons accelerated, smashing into phosphorescent atoms in the screen and producing light.
Allerede før den tid så mente Birkeland at dette måtte være noe som var analogt med det som skjedde mellom sol og jord. At det gikk katodestråler ut fra solflekkene og traff da jorda og skapte nordlyset. Denne sammenhengen mellom sol og jord, den hadde ligget der en stund, fordi man visste at når det skjedde store eksplosjoner på sola, for eksempel den I 1859, som var aldeles voldsom, så fikk man en stor magnetisk storm etterpå. Og utifra det så trådte Birkeland den slutning at sol og jord på denne måten hang sammen, og at det var katodestrålene som laget dette. At det også da måtte være en elektrisk spenning mellom sol og jord som sendte disse strålene.
Birkeland reasoned that this might be exactly what's happening with the aurora. He basically felt that electrons coming from the sun would be channeled by the Earth's magnetic field into the atmosphere, where they would hit the atoms in the atmosphere, creating the fluorescent glow of the aurora.
Og der kommer det som den store idé han får, at strømmene kommer utenfra, fra sola, går ned langs magnetfeltet, kortsluttes I den øvre del av atmosfæren og går ut igjen langs magnetfeltet. Dette var en helt ny måte å tenke på, og det forbandt jorda med universet.
he wasn't content with just looking at this theoretically. He wanted to look at it experimentally as well. So he built a scale model of the Earth as a magnet, which he called a Torello, which was a metal sphere with a magnet inside. And he put it in a vacuum chamber, and he basically modeled the system of the aurora in the Earth's magnetic field.
Typisk for Birkeland var hans metodiske framgangsmåte i vitenskapen. Han angrep problemet med sol-jord-forholdene av mange forskjellige metoder. Han angrep den teoretisk. Han var en god matematiker selv, men han fikk inspirert Carl Størmer, en av hans yngre kollegaer, til å begynne å beregne hvordan disse partiklene beveget seg fra sol til jord. Han gjorde eksperimenter i laboratoriet for å se disse strålene, bygget disse Terella-kamrene med en magnetisk jord inne i vakuumkammeret, og hvor han da kunne se hvordan partiklene beveget seg fra sola gjennom jordens magnetfelt og landet på jordoverflata, da helst i polområdene. Han gjorde statistikk på dette, forholdet mellom sol og jord, og ikke minst, han gikk ut i felten for å observere tingene.
Birkeland's way of thinking was in direct opposition to what I would call over-specialization in science. He was doing a lot of different things, taking patents. He was thinking about cosmology and about small practical things. He was creating industries and so on. And I think the main power in his ideas when it comes to inspiration is in particular this aspect.
Han utvilsomt en av pionerene når det gjelder å bringe elektromagnetiske krefter og plasma inn i kosmologien. Og mange i dag har anerkjent ham som den pioner han var på det feltet. Og hans ideer om hvordan strømsystemene i jordas magnetfelt, i jordas magnetosfære det tilhører de klassiske ting i den moderne magnetosfærefysikk.
After his death, this whole approach of seeing the universe, as Birkeland put it, as filled with all sorts of charged electrical particles, basically fell away. He didn't have descendants, intellectual descendants who would pursue this avenue of approach.
Etter Birkelands tid så oppstod det en annen idé om at disse strømmene var skapt var rent horisontale, gikk rundt i horisontale baner i atmosfæren. Og det var først og fremst Sidney Chapman fra England som var talsmann for dette. Han tilhørte de som var rene teoretikere, hadde ikke gjort noen observasjoner selv.
Chapman's approach, which is similar to that of many of the Big Bang theorists today, was to take a purely mathematical approach and say, what is the simplest way to express phenomena mathematically? And basically, let's try and fit the phenomena into that simplest mathematical expression. Well, he found that it was very difficult to precisely define the sort of mathematical three-dimensional currents that Birkeland had hypothesized. Remember, this is long before the development of computers. So he found that the easiest mathematical representation was if the currents were all confined to a sphere that extended little beyond the Earth's atmosphere. And therefore he started to model things on this model, which completely contradicted the idea that these currents flowed from the sun and were trapped in the three-dimensional structure of the Earth's magnetic field.
Etter sin død i Tokyo i 1917 ble Birkeland stort sett glemt, også i den vitenskapelige verden. Men han må utvilsomt ha inspirert noen. Han var en inspirerende person. Han skapte aktivitet omkring seg, han sprudlet av nye ideer, og han inspirerte sine medarbeidere. Han inspirerte utvilsomt også noen i sin ettertid, og en av dem var Hannes Alfvén i Sverige, som grep fatt i Birkelands ideer om vekselvirkning mellom jordas magnetfelt og universet, og utvikle sin magnetohydrodynamikk, og kom i sterk opposisjon til Chapman på grunn av det.
Hannes Alfvén simply felt very much in spirit with Birkeland in this respect. Hannes Alfvén was an engineer from the start, and he liked to think about everything as an engineer and not in very abstract terms.
And he realized that it would be impossible for electrons alone to flow from the sun to the Earth. It had to be plasma flowing, because if the sun gave out a flow of electrons, eventually it would become positively charged, and that would prevent the flow from continuing. So his theory was that there were ejections of plasma from the sun. When these blobs of plasma hit the Earth's magnetic field, they would distort it. And if the distortion was enough, you would have things called magnetic storms.
It took many years before Alfvén's work in this area was recognized. And the main reason is that his work was so simple and so obvious that even the brightest people did not really realize the impact what he was doing.
He also developed at this time a more elaborated theory of how the electric currents concentrate themselves. Because of course when you look at the aurora, it isn't just a continuous glow. It's this fine sheet of filaments. And these filaments, Alfvén knew, occurred because of what's called the pinch effect, which is if you have currents flowing through a plasma, any plasma, the currents produce magnetic fields. The magnetic fields interact with the currents in such a way the currents are attracted to each other. So if you start out with an even distribution of current, the current will filament. It will become tiny concentrated filaments of current pulled together by their own magnetic field.
The essence of magnetohydrodynamics is to boil down the very complicated motions of plasma particles in magnetic fields into a simple model that visualizes the plasma as a fluid that is electrically conducting. So it simply is a fluid where currents are allowed to flow, and the currents are interacting with the electric and magnetic fields and dragging the fluid with it. Another way to see it is that the fluid is dragging the magnetic fields with it. And this simple picture to visualize things had an enormous impact on how we could understand phenomena in space.
So he developed this pretty elaborated theory, which was compared with both laboratory experiments and observations of how the aurora works. But Chapman was still the dominant theorist, and Chapman completely rejected his theories and in fact won't even discuss it with him.
Det viser seg at det ikke er mulig å skjelne mellom de to ideene på rent observasjonsmessig grunnlag på jorda. Vi måtte ut i verdensrommet for å avgjøre hva som var riktig. Og det var det som skjedde utover på 1960-tallet, hvor man oppdaget at det faktisk gikk elektriske strømmer langs magnetfeltet, og man kalte dem Birkelandstrømmer.
Johannes Alfvén is generally credited as being the father of modern plasma physics. And he was, of course, awarded the Nobel Prize in 1970 for his extremely varied work in plasma physics. Now, by the time that satellites and space probes had begun to demonstrate that Alfvén and Feldhammer's and his colleagues' ideas about currents flowing through the solar system were correct, that such currents really did exist, and people began to accept that these currents, much stronger currents during the early days of the solar system, actually had a role in the formation of the solar system, in compressing gas and dust down to form both the sun and the planets. By that time, Alfvén had started to move on to larger scales.
Alfvén was very eager on formulating very bold theories for cosmology, and basically rejected the Big Bang model, and in this way came very much in opposition to the mainstream of cosmology.
Because he reasoned that if these currents flowing through the solar system could have formed the stars and the planets, then could not have much larger scale currents also be the way that galaxies themselves form. Some people have said that science is a method for asking questions of nature. And if that's true, then we can say the Big Bang supporters are people who won't take no for an answer.
Over the last 2 or 3 decades, the Big Bang theory has become increasingly more and more speculative. One expects from a scientific theory definite predictions which can be tested by observations. If the observations disprove the predictions, the theory is supposed to be disproved, and it should be modified or abandoned.
In science, we work from observation, from empirical observation that starts in the here and now and works outwards and backwards. The Big Bang starts from mathematical formulas, deductions, that start from the beginning of the universe and to try and predict it forward. This is the same mathematical approach, mathematical deductive approach, that led 2,000 years ago to the development of the Ptolemaic universe. The universe, of course, which was Earth-centered, with the planets going around the Earth, with the stars in a crystalline sphere. What these theories have in common is that they try and derive what should be the universe based on what perfect principles we can develop, what God should have made the universe to look like. And then they try to fit the universe into that perfect framework.
However, what has happened over the years is that whenever observations have come up which don't agree with the predictions of the Big Bang theory, the theory adds an extra assumption which is not at all tested, which is not at all resting on conventional physics, and simply assumes that that must be true.
The problem with that is that develops myth, not science. It develops a religious faith in which nothing in the real world, in the observable world, can contradict the faith in this structure, in the Big Bang. This undermines the entire scientific enterprise. The reason science has been valuable to human beings is because it allows us to predict nature in such a way as we can use nature in a predictable fashion in technology. To abandon this approach, which has served us so well, and to go to the idea that we can deduce, we can read the mind of God, as Stephen Hawking says, and deduce from perfect mathematical principles what the universe must be, is to abandon the scientific
There are those who would say that the story which follows could happen only in a dream. Regardless of where it could happen, this is the way it did happen in this rather strange and out-of-this-world office. Whitey is entrusted with the records of good salesmen. Red, the other kind. Now, it seems that Red and Whitey never see eye to eye on matters. Naturally, this leads to many arguments.
I am the door. By me, if any man enter in, he shall be saved. There is only one door to heaven. People would have us believe there are many doors to heaven. No one can enter with a heart of unbelief. Only a heart that believes will have entrance there.
I'm going to keep a pretty close watch on these guys.
And so will I.
This idea of the Big Bang, which did originate at the beginning of the 20th century, the reason why it is so widespread nowadays is that it has a deep connection with the biblical creation. Instead of saying that the universe was created by God like 4,000 or 6,000 years ago, they now say it was created 10 billion years or 20 billion years. So for most people, and also for many scientists, they see a connection between this creation which comes from the Bible and this scientific point of view.
In 1952, in August 1952, we had a meeting of the International Astronomical Union in Rome. And we were received by the Pope. The Pope was then Pius XII. And Pius XII made an address to the astronomers. And this address was very clear. He said, oh, the Big Bang is the Fiat Lux, and how beautiful is the astronomy, how it proves that the greatness of etc., etc., etc. And I've been always sort of an heretic in all that sort of things. I don't believe in any God. And having the Fiat Lux and the Big Bang associated each with the other made me suspicious from the very beginning.
Nowadays, the majority of the physicists and astronomers, they believe and they work with the point of view of the Big Bang, according to which the whole universe did originate out of nothing, like 10 or 20 billion years ago, in a Fiat Lux, in a moment of creation. There was nothing before, and then the whole universe did appear and then begin to expand and to grow, and our galaxy, our life came out of this great explosion in the past. But I myself, I had always problems with this point of view because they are somewhat against the principles of physics, the most basic principles of physics, which are related with the conservation of matter, and conservation of energy.
Yeah, I forgot completely about the Big Bang because it just didn't interest me to look in those distant things of which the physics was rather vague and difficult to observe. But let's face it, in all the story of astronomy, for years and years and centuries, the progress came from new observations and from confrontation of those new observations with past theories, contradictions, sometimes no contradictions, sometimes just a confirmation, but most often the contradictions led to new progress, to changes in the theories.
In standard Big Bang cosmology, you have what I call a series of epicycles. The Greeks used to have epicycles, which are known as circles whose centers move on other circles, whose centers move on other circles, in order that they could correctly describe the position of a planet at any given time. They found that in some cases they had to introduce many circles before they could get anywhere near the reality. These epicycles are the assumptions that have been put in ad hoc into the theory from time to time.
The way that the Big Bang has handled the cosmic microwave background is a very good example of how this process works. When the cosmic microwave background was discovered in 1964, this very smooth, even radio radiation coming from all directions at once, the smoothness of the microwave background was considered a proof of the existence of the Big Bang. Only a universal explosion, they argued, could create this smooth, even background.
Now this is not necessarily so. Actually, the 3-degree radiation, to me, has not a cosmological value. It is observed in any cosmology. In any cosmology, you can predict the 3-degree radiation. So it's a proof of no cosmology at all if it can be predicted by all of them.
There's no explanation at all of the microwave background in the Big Bang theory. All you can say for the theory is that it permits you to put it in if you want to put it in. So you look and it's there, so you put it in. It isn't an explanation.
First of all, the temperature of the microwave background, basically the amount of energy, was not what the Big Bang supporters had predicted. They had predicted a much higher temperature.
So it was 50 degrees Kelvin that was being compared against the 2 to 5 degrees Kelvin from the steady state universe. Now this may not sound like much, but in energy density, where we measure the absolute differences, the differences is 4 orders of magnitude, 10 times 10 times 10 times 10 difference. So there is an enormous difference between 50 degrees Kelvin, a rather poor indicator of what is happening in the universe, and 3 degrees Kelvin.
When you read the textbooks, they don't tell the whole story. They don't present these figures, 5 greater than 5, 7, 50, and then that they did find 3. So that's very strange how the textbooks, they hide a part of history.
And the temperature of the Big Bang proponents was rapidly readjusted from 50 degrees to 3 degrees.
But their theory could be adjusted so that the temperature becomes a free variable that could be just taken as what was observed.
We have an observable universe which is made of stars, galaxies that are not very distant, and that's all, because the 3-degree radiation, I would even think that it might be local. Still not. And going beyond that is, I think, a wild extrapolation, whatever it is. And the physics that we could imagine to be existing there is based on nothing, because we have no test for it.
Although Big Bang advocates claim the discovery of the cosmic microwave background radiation as conclusive proof of their theory, History actually shows that there is a long line of well-hidden predictions previous to those made by Big Bang theorists. Not only were these predictions prior to those of Gamow and associates, but more importantly, they were made without any need for an expanding universe, and with far greater precision. This shows us that observations such as the background temperature of space have no preference for one or another theory, and therefore may not be used as definitive proof of any particular model. The fact that a theory is able to describe an observation does not mean that the observation proves the theory.
This is Bob Wilson at Bell Laboratories. The noise you're listening to is noise from a radio astronomy receiver on the 20-foot horn reflector antenna. This is the original instrument with which Arno Penzias and I discovered the cosmic microwave background radiation in 1965. This radiation comes from all directions and has a thermal spectrum. It sounds, therefore, very much like the noise you would hear on an FM set or a TV set which is tuned to an unused channel. Unfortunately, only about 10% of the noise you hear is coming from the cosmic microwave background radiation. The instrument is contributing about 22 degrees of noise. The Earth's atmosphere is contributing another 4 degrees. Our Milky Way galaxy is contributing 1, and finally the cosmic microwave background radiation, another 3 degrees.
When you say that the microwave background is a perfect black body radiation, that means it is completely thermalized. The theory of black body radiation tells you that that is the ultimate state of radiation when all information of sources from where radiation came has disappeared, because thermalization means that it's completely smoothed out, wiped out its sources.
One of the main things that people point to as confirmation that the Big Bang is a valid theory is its predictions of abundance of the light elements. This confirms that the theory is a good theory. But in fact, it doesn't. In fact, observations clearly contradict this prediction of the Big Bang. Big Bang predicts the abundance of 3 elements: helium, lithium, and the isotope deuterium, which is the heavy isotope of ordinary hydrogen.
Now, one of the conclusions from this particular hypothesis that you can make deuterium in the Big Bang was that the density of matter in the universe should not exceed a certain value. Now, over the years, in the 1960s, this seemed to be holding out. 1970s, it seemed to be holding out. But by 1980s, it had become clear that the universe has considerable amount of dark matter, which is not included in these calculations. Now, if you include all this dark matter, you exceed the limit that deuterium abundance has put. That means if you assume that all the dark matter is present, then you could not have made deuterium in the amount that is observed in the universe. So this was a way of saying that the Big Bang prediction was wrong.
To determine the density of the universe and see whether this is consistent. If the theory is right, the density of the universe determined from deuterium abundance, the one determined from lithium abundance, and the one determined from helium should all be the same number. There can only be one density of the universe, while actually that's not true. Again, these are gross contradictions, and yet again, it doesn't cause the abandonment of the theory. Big Bang theorists simply say, well, there must be something that we don't understand about the evolution of lithium, about the evolution of deuterium, and even though these predictions have steadily diverged over the course of time.
But what did the Big Bang proponents do? They wanted a way out, so they said that this extra matter, which is proving to be awkward to fit into the framework, has to be a strange kind of matter, which is often called non-baryonic matter. Non-baryonic matter is basically matter which is not made of protons, neutrons, and the kind of elements that we are made of here on the Earth, or which we see in the stars or in the interstellar medium.
Dark matter. What was dark matter? Dark matter was some matter that we don't understand. We don't know what it's about. We haven't observed it. But it isn't ordinary matter, so it doesn't enter into our equations about the light elements, and we can't see it as stars. But dark matter is 90 or 99% of the mass of the universe. This is what we call in science a fudge factor. When your equations don't work out, you just write in this little plus something. Well, in this case, this was a humongous fudge factor because it was 90 or 99% of the universe.
And you have to not only postulate that this matter has to exist, but it has to exist in quantities much greater than the amount you see of ordinary matter.
And I should emphasize that people have looked for dark matter. People have looked for dark matter since it was proposed 20 years ago. Axions, WIMPs, little particles that are supposed to be floating around in space that we should, in theory, be able to observe as they pass through the Earth. Dozens of experiments have looked for these particles. Not one has been found. Again, this should be a contradiction. The way science works, you make a prediction, observation contradicts it, the theory should be rejected. But that hasn't happened. And the epicycles don't end. There's a problem with dark matter, even theoretically. Even though we can't observe it, there's still a problem with it, which is dark matter slows down the expansion of the universe. So the length of time that the universe has existed, the length of time since the Big Bang, should be shorter than what's indicated just by linear expansion. The problem is it's too short. The prediction of the cold dark matter theory is that the universe should be about 8 billion years old. Well, that's a big problem. We can determine the age of stars in our own galaxy, in the oldest globular clusters, both based on very well confirmed theories of the nuclear evolution of stars and spectroscopic observation. And the stars in our galaxy are 13 or 14 billion years old. So it's very embarrassing to have 14 billion year old stars in an 8 billion year old universe.
In addition, they went into dark energy. Now, why did dark energy come in? Because if you take the present value of the cosmological constant and the cosmological constant which came out of inflation, you find that they are not the same. Not only they are the same, but you have to find that the difference lies in something like 108 orders of magnitude. Now, can you imagine a physical theory getting the answers wrong by a factor 10 to the power 108? Yet, the Big Bang cosmologists very coolly accept this and simply put in another epicycle by saying that there is a dark energy which has changed over the time by this factor. So we have to accept that.
Dark energy is some force, again, unknown on Earth, unpredicted by any theory that we have validation of here on Earth, that causes an acceleration of the expansion of the universe. So as the universe is accelerating, and it's older than appears on the basis of the dark matter theory, and it's 15 billion years old. So we solve the problem of the age of the universe by hypothesizing yet a third completely ad hoc epicycle dark energy. So now we have a universe which is 70% dark energy, 28% dark matter, and only 2% matter that we can observe through our telescopes and here on Earth. Epicycle is being piled onto epicycle. And in the process, what we call the predictive power of the theory is fading away to nothing. One of the most destructive features of the methodology of the Big Bang is that it conveys the idea that only experts can understand the universe. Only people versed in extremely complicated mathematics can understand the universe. That if dark matter, dark energy appear to be incomprehensible or even nonsensical, it's because you don't understand the mathematics of these complex equations. This is, of course, the argument of the emperor's new clothes. If you can't see the emperor's new clothes, then you must be either stupid or incompetent.
So this goes on, and we can find that the old Greek tradition of epicycles, which was even adopted by Copernicus and has been continuing in standard Big Bang cosmology. If we go by the history, the Keplerian orbits, which were elliptical orbits, very cleanly and neatly resolved the problem of planets. And the circles upon circles idea had ultimately to crumble down. Now, in the same way, I suspect that the Big Bang theory will collapse under its own weight of assumptions, and a more neat theory, neat interpretation of the universe will emerge.
Does this mean that the age of the universe is not what Big Bang theorists have implied? Could the universe be eternal after all? How much are cosmologists really able to know?
We are now in a stage which can be called a plasma universe. And we are simply not privileged to know what stage the plasma universe evolved from. We do not have privilege to that information. We do not know. We will never know. And this is one major difference between the plasma universe cosmology and the Big Bang cosmology that claims to be closing in on the final answer.
The universe described by plasma cosmology is quite different. Here we are talking about a universe with no beginning and no end, an infinite universe, continuously evolving, an evolution that is continuously increasing at an ever rapid pace. It is a universe in which there is a coherence between what we can understand in the here and now on Earth and what we can understand in the rest of the universe. A universe in which there is no real limit to our ability to understand more new phenomena. And a universe in which we can apply what we learn in the universe in present-day technology.
The basic difference between plasma and all other forms of matter, that is solid liquids and gases, is that a plasma produces electromagnetic radiation and also tends to filament. So that we would expect in a simulation, which is what we see, in an experiment, which is what we see, we would expect to see throughout the cosmos a filamentary structure that is a spaghetti of currents intertwining the cosmos.
We can use plasma theory derived from experiments in the laboratory, from the basic concepts of plasma instabilities, from Maxwell's equations, and from the well-known laws of gravitation, to describe and predict how the structure of the universe came into being and what that structure is. So the key question is, how could this structure come into existence? Now, in the Big Bang theory, the universe starts out extremely homogeneous, very smooth.
This was direct contradiction to the plasma universe that insisted that the universe overall must be filamentary.
But what we have today is extremely clumpy matter. When I talk about these huge voids, the structure of voids, the matter inside the voids is less than 10%, perhaps less than a few percent as dense as the average. And the matter in the walls of these voids, where these filaments of superclusters of galaxies are located, is 10 or 20 times the average. So you have extreme clumpiness. Now, what's the problem for the Big Bang to explain this? There's a huge problem. There is not enough time since the Big Bang to form these structures. These structures are older, much older, than the time hypothesized since the Big Bang.
Now, again, in interpreting the observational information, we can again go to the laboratory, which we are privileged to diagnose in any number of ways, in any number of directions, and run any number of experiments, which you can't do with the universe. But we also turn to the supercomputer simulations. Now, what a simulation does is that it allows you to model the plasma, regardless of size, put in the rather few basic initial equations, and then follow the simulation through its various nonlinear stages and the different morphologies or shapes that the plasma will take.
In Tony Peratt's simulations, as the current spirals into the center of the galaxy, turns around and moves out along the axis of the galaxy. In that central area where the current is extremely concentrated, there seemed again the potential for violent events. And Alfvén and Peratt raised the question, couldn't this be a way of explaining the extremely violent events that occur in the center of galaxies that are known as quasars, in which huge amounts of energy are released in what, by astronomical terms, is a relatively small amount of time. That is, millions of years compared with the billions of years galaxies exist.
Initially, the time frames shown represent 1 billion years or so, but now we're going to carry it out for 10 billion years to see what happens to these double radio galaxies or quasars as the two filaments have evolved into. And you'll see that the tails start to elongate, and fairly soon you're going to start to see a spiral structure. And as we get closer to the 10 billion years, the end of the movie, you will see that we have formed the shape, the morphology, the shape of a spiral galaxy.
Now, Alfvén developed a number of concepts that were critical to the whole understanding of the plasma universe. First of all was the basic concept of scale invariance in plasmas. That means there are certain phenomena in plasmas that don't change regardless of whether you're dealing with a laboratory scale of centimeters or a solar system scale of millions of kilometers or a galactic scale of hundreds of thousands of light years. What that meant was that time scales the same way as distance does. So not only does this mean that the phenomena of the cosmos can be studied in the laboratory, but because of time compression, the phenomena of the cosmos are essentially transient phenomena. It's funny to think of a galaxy lasting billions of years as a transient phenomenon, but it's analogous to events in the laboratory that last only millions of seconds. Another way of putting it, the plasma universe is extremely dynamic.
It's not going to be hypothesis. We've moved further than hypothesis. We've definitely gone into the second lake, the analysis, and we're well towards the third lake.
Now, we haven't reached the third leg, of course, and perhaps, well, you can't with the universe because you can't experiment with the universe itself. Now, of course, we, like Alfvén, his idea, indeed you can determine what's happening in the universe in an experiment, but as far as producing universes, well, we're not going to do that. So we're going to do the best we can in the laboratory.
The universe that the Big Bang envisions and the universe of plasma cosmology are very different universes, and they have very different implications, and they cohere with very different ideologies of what is happening here on Earth.
The Big Bang theory will collapse under its own weight of assumptions, and a more neat theory, neat interpretation of the universe will emerge.